Hello, this is Jeffrey Fox again. This is the last slide set on going further than Hadoop presentation, and this one is just some measurements comparing these various technologies, Twister2, Spark, Flink, and MPI. And these are likely to get improved because we keep building more capabilities in Twister2. And we're planning a lot more performance comparisons of things like the data flow graph execution and other aspects. These are more focused on the communication subset of these systems. So this was a study we did some time ago we'll have repeated with more modern versions of the technologies. Where MPI doesn't change very much, but Spark and Flink are improving. And we looked at three machine learning algorithms, or at least two of them machine learning, multidimensional scaling and k-means. And TerraSort is not particularly so much a machine learning algorithm, but it's what it is, sorting large data sets. We had three runtimes, three algorithms, and the implementations are mainly in Java. Yeah, oh, I don't know what. And MDS is particularly challenging for these systems because it's a complex parallel algorithm with multiple different components. And this is, although you can say this is not realistic at the moment because most things are pretty simple, my expectations is that life will get more complicated because that's what's happened in the past. Because as you study things, you find better ways to do it, and there's ads and all of things, and the approach gets bigger and bigger and more complicated, and that's actually the challenge. That's why MPI is actually successful, because people can still understand it, but these automatic systems cannot, and that's what happens with MDS. The automatic systems do not understand it. K-means is reasonably simple. There is an iteration with one iterative loop, and TerraSort has no iterations. These are written with Java. Typically, the Java gives comparable performance to C, but if you don't do careful work, which we documented in papers, Java actually underperforms C or C++, or even, of course, Fortran. So here we have results from multidimensional scaling, which I mentioned was the most complicated. It has three nested parallel sections, which is not terribly unusual for a parallel code. I wouldn't view it as the hardest code I've ever written, but it's certainly much more complicated than k-means, and that's because it has a temperature loop, a loop iterating expectation maximization, and a special internal loop to solve matrices. And those three separate parallel codes confuse Flink and Spark, which is sort of aimed at one level of complexity. They don't understand this hierarchical system. Notice Flink is the worst here. Here we're looking at the performance as a function of the number of points on 16 nodes. And notice that MPI actually gives similar results for the compute part only and the compute plus communication, showing the red, which is the communication included, is the communication must be a negligible part of the whole time. Whereas with Spark and Flink, communication or synchronization dominates. If we look at the behavior on the number of nodes, then MPI, as we hoped, gets better as you increase the number of nodes, whereas Spark and Flink actually get worse as you increase the number of nodes. So this is not good for horizontal scaling, it's horizontal descaling or something. There is something quite amusing. You might try to find open womb pregnancies, and you will find that's a rather flippant approach to modern technology. So here we have an explanation of one of the reasons this happens. If we look at MPI and do a communication thing here, or reduce, you will find that processes just run forever. And then as you do the or reduce, that is done in a cunning binary tree which is carefully done in parallel, so that actually the end result is that all nodes get the all reduce at the end of the action. Now, if I do the same thing with Spark, we don't do this binary tree. We do it separately on each node, using possibly combined to do it with inside a node. Then we have to just send everything to a single place, maybe to dump it on disk, or in the case of Spark, just to do it maybe won't be dumped on disk. It will be done in just sent to the reduce process. The reduce process is a different process, like in all MapReduce. In MPI, there is not a different reduce process and map process. They're all the same process. And then after we do that, we just have the answer in one place, wherever the reduce node is thing, and we have to send it back. So this is a much more complex process with lots of overheads compared to this very elegant, simple. Well, it's actually not so simple to invent, but once you've invented this particular elegant algorithm, it's quite simple to look at. So this is what I mean by in place. MPI is in place. We just sit there in the same processes and let everything rattle around. Whereas Spark and Flink and Storm and Heron do everything in a distributed fashion. That's an important difference, and we have to do both, because for some problems in place is good, and for other problems, like we're going from the edge to the cloud, we better not do it in place, because they're maybe hundreds of miles apart or more. If we go back, look more generally at machine learning, everything started off with Mahout. That was Hadoop's machine learning library based on MapReduce. Then Spark replaced Hadoop, and MLlib replaced Mahout. And then we developed the HARP system, which is got optimized machine learning. This is in a project called Spidle, which has various community algorithms, biomolecular simulation, network science, and image processing for pathology and polar science. What we have here is original Mahout machine learning, a lot of the basic ones, collaborative filtering, logistic regression, hidden Markov models. You see, they're all deprecated because they don't run well. K-means of various types. And other clustering algorithms. There are many clustering algorithms because clustering is a heuristic. So you do it, you can do it in different ways, and different ways have different performance on different problems. So you need to choose the clustering algorithm suitable for your problem. If we look at HARP and the associated Spidle algorithms, it's got quite a large collection, around 20 here, and there may be more by now. Or there are more by now, and these are all built around the concept of collective operations, in-place collective operations. In place means it's like MPI. HARP itself is not MPI, but it has the same in-place philosophy, and there are these magic, these well established but not always implemented collective things, or reduce, rotate, and so on. Not all of them have been implemented with the Intel node libraries, which allow optimized performance, exploiting especially the vector operations of Intel. Intel chips have up to 512 bits of a vector operation, which gives them significant performance improvements, which in the latest version of Intel allows, for instance, 32 floating point operations per clock cycle. Here is some examples of what clustering looks like. This problem is a proteomics problem, and these are measurements of peaks. And you can see here the yellow are the centers of the clusters. This particular problem had some huge number of clusters, and this is a very small sample of the data set. And you can see that this is actually a two-dimensional problem, so this is you're seeing actually the real complexity as it is here, and the stars here are points which aren't clustered. They don't seem to fall into a cluster. They're just isolated. They could be just a cluster with only one point in it. The red dots are all a single cluster here. and the yellow points are the centers of the clusters. So you can see it's actually, this already illustrates a little bit of an issue. Let's look around here with, you can see there's a whole set of points which is divided into multiple clusters because we happen to know the typical error sizes, so we know this can't be one giant cluster. And it's not so clear that that particular decomposition is correct. This is typical of many clustering problems, that you have points which are closest together, and whether they represent one big cluster or several small clusters, or if there's several small clusters, how exactly you chop them up. It's pretty undefined and difficult to do. Here is another example of clustering. This is actually gene sequences, so it is not two-dimensional, it's multi-dimensional, thousands of dimensions maybe, because you can't map gene sequences naturally into 2 or 3 dimensions. So we've done clustering, which is the coloring. Each color is a different cluster. What we're doing here is a variant of k-means, a pretty sophisticated variant, which has much better performance on this type of problem. And then we've mapped it into actually 3 dimensions, but we've shown the result in 2 dimensions. And you can see here that actually these clusters are reasonably clear. They're not, because it's multiple dimension, they're actually separated in the 3rd dimension. And these clusters are not really on top of each other like they were on the previous slide. So if we look at k-means in detail, so you choose a number of centers. You assign either randomly or thoughtfully cluster each point to a cluster. Then you iterate, assigning each point to the cluster that's nearest to it, or use the initial choice when you start. Calculate the new center of each cluster, the mean of the assigned points, and then look at the change from the previous iteration and stop if that change is small enough. And there are lots of variants of this to speed it up and to clean it up so that it doesn't, for instance, here you have to guess the number of clusters. There are the variant I showed you with, actually both the variants I showed you before on the previous slide, the program was using a version of k-means that actually determined the number of clusters. And notice that all you need for this is a distance. This is a pretty interesting point about machine learning. You have to define distances in your space. And that's pretty important to be able to have experience in how well to define distances. Because like in that, in the first one, the proteomics, it was a 2-dimensional space, Euclidean space, and so it had a natural distance. Just had to scale it properly to avoid differences in scale confusing you. That's a usual thing. You usually scale everything, so all dimensions have means of 0 and standard deviations of 1 for the points in them. But in the DNA case, DNA sequence case, the second cluster I showed you on the previous slide, then that doesn't have a natural distance, and we use some variant of a Smith-Waterman algorithm, but whether that's the right distance is not clear in the various variants because it has not got a clear Euclidean space attached to it. Here is just the k-means problem in Spark, showing it is pretty easy to program it, and it's a good thing for people to look at. And here is actually I started off with MDS, but the same study did do k-means. Here is MPI. Here is Flink, and here is Spark. Again, Spark outperforms Flink in this case, and actually in this case here, you do get some performance increase as you increase the number of nodes, but MPI does better. Remember, in MDS, you actually got worse as you increase the number of nodes. So this is actually, you see much better results from MDS, and that's because the automatic data decomposition the Spark and Flink does works okay for k-means. It just doesn't work okay for MDS. We're actually going back and forth between different decompositions for different parts of the problem. This actually has Twister2 on it. Here's MPI, now is blue. It was red in previous slides. Twister2 is red, somewhat slower than MPI because it has overhead. That overhead disappears as the problem gets larger, because then you do more computing, and so sort of overhead is less important. That's a well-known feature of all parallel computing. The bigger the problem, the smaller the overheads. So this is the latest version of Spark. And you can see MPI and Twister2 do much better than Spark. But not, this is only factors of 3 or something. So that is not like the orders of magnitude we saw in the MDS case, 2 orders of magnitude. Now we come to some pictures of the overall structure. Here's HARP-DAL. We have the machine learning applications and the data analysis invoking multiple machine learnings. We have the HARP computational model. It defines an interface, because remember, normal big data have key value pairs, but key value pairs are not the natural interface for most scientific problems. You need images or cluster centers and things like that. Then we have the model, the data, and the model parameters, which are shown both here and here. Then need to interact with the data. Remember, I told you, machine learning has big data and potentially big model. Then we have HARP's communication model. Then we have Intel's DAL kernel, which is making all these things run fast on the node and using vectorization. And Intel's kernels invokes other kernels. And we tested this on Haswell and Knight's Landing and got good answers. This shows you the collective communication, how different the different reduction operations correspond to different structures of communication between the nodes. That's what a collective communication is. A collective communication is one where you have lots of processes running on a single job, and the processes just get together, and in general each process sends to every other process or a subset of every other process. So collective means they're all doing things together, and we have different ways of doing that. Reduction is one, broadcast is another, gather is and scatter and these other ones, regroup. They're all variants of more global transformations where data flows from one node to multiple other nodes, and all of that happens simultaneously for all nodes. Here's our HARP on February, and they're all available in GitHub actually for now. This is February 2017, and that's stuff. So they've been open source for 2 years, and we have these 12 well-developed applications. Here's HARP's comparison with some of the competition. Here is the original comparison of HARP which is running real fast because it uses DAL for node performance and MPI effectively for internode performance or a variant of MPI. And so here's HARP versus Spark on k-means. Here's HARP versus PyTorch on principal component analysis. And this is the hardest application. HARP versus MPI on subgraph problems. Subgraphs are the hardest ones to do. Graphs in general are the hardest because they have such irregular connectivity, and subgraph is finding subgraphs of a particular structure. You think of a template, which is the simplest is a triangle, 3 graph nodes connected together, but can be much more richer template. This is a 10-node template, and this is a 12-node template, and it's very challenging to take big data sets and find all instances of these templates. But if you have a particular model for terrorism or the structure of an activity, then you want to see how often this template appears in your data set, because then you can find similar similar activities within your complex data set of interpersonnel or inter-organization or inter-entity interactions. We've already pointed this out, how Twister has Twister.net and box synchronous processing, which is using TCP or MPI, and can also use HARP. And we have this new DFW, the data flow node. And here we can see how actually DFW does data flow reduction. It does it using, because in data flow you have different source and target. At the final stage, DFW separates the reduction from the maps. These are maps are here. Whereas in BSP, maps and reduced nodes are identical. DFW has pretty interesting features. It does key-based operations. Everything can be based on key selections. It's done at the data level, not the message level, whereas in MPI, if you have lots of data, you have to break it up into messages. And I say it's critical for DFW that you have target tasks, which can be either the same or different from source task. And everything is dynamic, and it also supports streaming. All right, so this actually compares Twister.net again directly on Spark and Heron. Spark is k-means up here, and Heron is various the basic operations: reduce, partition, breaking up the data, and broadcast. And you can see that the Heron, which is the blue thing, is always runs slower than DFW. DFW has two numbers. It either uses the built-in Ethernet, or this particular machine's actually rather old. It has an old 1 gigabit per second Ethernet, but it also has InfiniBand, which is much faster. So here you have InfiniBand, but here you have a comparison on the same network, the 1 gigabit for Heron and Twister2 DFW communication. Up here we have Spark, and Twister2 uses either the DFW or the box synchronous processing, and you compare k-means either as a function of the number of centers, or as I said before, in the number of nodes. Actually, Spark doesn't even scale here correctly on this particular one, and Twister.net clearly scales nicely, and you don't see much difference between BSP and DFW, which says that DFW is written pretty well in our case. So the slowness you saw in Spark and Flink was not due to using data flow communication as we first thought. It was using poor data flow communication. Okay, here we show a Flink and Twister2 and BSP, which is effectively MPI for TerraSort. TerraSort, you will not see just big factors because it is not iterative. And we have here essentially a comparison on the total data set size, which goes from 32 gigabytes. Here we have 1/4 terabyte. Here we have 1/2 terabyte and 1 terabyte. But we only get results on Twister2 for all cases, and Flink is 1/4 terabyte or lower. Everything is going to disk as necessary, and we can see that for small data sets, MPI does the best, like this, and for large data sets, actually, DFW does somewhat better. Maybe because it handles the large messages better. We have various communication mechanisms. We can either use the 10 gigabit per second Ethernet on this particular machine. It's more modern than the previous machine with 1 gigabit per second. And we can also use InfiniBand, which is, all these machines have InfiniBand and Ethernet communication. IP over InfiniBand effectively allows classic TCP/IP, which is what Flink implements everything with, to run on InfiniBand. And you can, for the Twister2 case, and the MPI case, which is under our control, we've broken it up into the communication component, which is blue here, and the rest, which is a sort of greenish color. We haven't got that decomposition for Flink, or nor do we have it for the larger data set sizes. So then these things here are just InfiniBand. We just use InfiniBand for the Twister2 case, which is the MPI case, and the DFW. So if you look here, we see good solid results with DFW being pretty competitive with MPI, and possibly for small messages, the lower latency probably of MPI is seen in the results. Here we have Flink and Twister2 on reduce and partition operations, which are core communication capabilities, and we have results on IP over InfiniBand directly, or for with the 1 gigabit per second DFW, which is this. We did the same for Heron. The Flink is actually running on InfiniBand using IP over InfiniBand, and the core InfiniBand is always giving you the best answers. And here we have Flink on 1 gigabit, DFW on 1 gigabit, Flink on IP over InfiniBand, which is significantly better than the 1 gigabit. Here's 1 gigabit for Flink. Here is 1 gigabit for, here's IP over InfiniBand for Flink. Here is InfiniBand for data flow. And this is data flow running on 1 gigabit per second. So the partition operation, you don't get such big effects, but always actually the blue, which is the optimized DFW, is always actually the fastest. So it's not such a big effect to say the reduction or some of these complex iterative algorithms, MDS and the k-means, but still you see that our system is faster. And here we look at not at the overall bandwidth utilization for Flink, Twister2, and BSP, which is the Open MPI technology which we use usually. And here's what the bandwidth you're getting in communication, with MPI doing better on the 40 gigabit per second network, and we have the 1 and the 10. This one here, the 40 is InfiniBand, the 10 is the 10 gigabit per second Ethernet, and the 1 is the 1 gigabit per second. And you can see that there's not a big difference between them, except for the case of InfiniBand, where DFW and the Open MPI give much better results. That's just for bandwidth utilization. We already showed that when you put them into a real actual primitive, such as reduce, then you actually got much better results for the Twister2 technology. So that's the last slide of this set, which shows that Twister2 has encouraging performance compared to the default big data systems. Thank you very much. That's Jeffrey Fox signing off. No more on more than Hadoop.